Hello, everyone. So, today we're going to be talking a little bit more specifically about a more unfamiliar type of mass balance. That's going to be atomic mass balance. So, let's pull up our good old friend, combustion of methane. So, I've got my same feed of 10% methane and 90% air. Let and we know it goes to 95% completion. So, I can solve the same problem with an atomic balance in, again, 4 steps. So, first one, same as last time, determine the number of moles of each atom instead of, which is only a single extra step on the number of moles of each molecule. Then, here comes a trickier one. Start trying to identify where each type of atom is located in the products. So, for example, nitrogen, N2 is the only species that contains nitrogen, and hydrogen is contained in water and methane. 3, identify the number of moles of molecular terms that we already know. So if there's any of these terms I already know, that can help me solve a set of serial equations for the molecular terms I don't know. So this one is a little bit more unfamiliar and a little bit trickier, though I have had many students prefer this method to solving complex reactive systems. So let's go ahead and walk through our example. So let's go ahead and determine the number of moles of each atom. So can't have combustion without carbon. So my moles of carbon in my reactants is entirely located in the methane. And I've got 1 mole of carbon per methane molecule. So this gives me 10 moles of carbon. Then for hydrogen, this is also again entirely located in the methane. Got 4 moles of H per mole of methane, so I've got 40 moles of hydrogen. And oxygen, entirely located in the O2. We previously solved this as 19.8 moles of O2, so this gives me 39.6 moles of oxygen. And then for nitrogen, well, this one's easy. The only source of nitrogen is nitrogen. So what we can then do is take twice of this and we get 140.4 moles of N. Now I need to identify which products contain which atom types. So my carbon output is going to be essentially the sum of the outputs of CO2 and methane, whereas my hydrogen output is going to be essentially 4 times my methane output plus twice my water output. My oxygen output is going to be twice my CO2 output plus twice my oxygen output plus my water output. And the total numbers of total N output is going to be twice the N2 output. And again, one of the useful things to make note here is that each of my atomic outputs is going to be the same as my atomic inputs, which I just solved. So these terms have already been solved. So now I can identify any terms that I might already know. So a good place to start is moles as my N2 output. That's simply I can rephrase it as half of the moles of N. So congratulations, we get back to where we started, what we covered last time, where I have 70.2 moles of N2 per hour as an output because there was nowhere else N could be. Now, the other term I can go ahead and solve is moles of methane, because I knew with a 95% conversion rate that I should have 5% the amount of methane in products as I had as reactants. So using that, I can go ahead and solve for 0.5 moles per hour of methane as my output. So that's everything I know. Now I can take those equations I generated in part 2 and solve them sequentially. So good place to start is going to be my moles of carbon. So this can be given as my moles of CO2 plus my moles of methane. Well, I now know this term, so this means that my moles of CO2 has to be the difference of 10 and 0.5, so 9.5. Similarly, since I have the moles of methane, this will generate the hydrogen term for methane, leaving only the hydrogen term for water. So I can go ahead and rearrange this equation as half of the difference in between these two terms, or 19 moles of water. And oxygen, little bit messier, because now I needed to have pre-solved my water term, which I just did here, and pre-solved my CO2 term, which I just did here. So the only thing left remaining is O2. So when we go ahead and solve this system, it simplifies down to 0.8 moles of O2 per hour in the product stream. So it's a little bit of a different metric, and I encourage you to solve problems you could normally do with an ICE table or with molecular balance to give a chance for atomic balance. Because as we're going to see next time, each one of these techniques has some serious advantages and disadvantages. So next time, a little bit of compare and contrast. Till then, take care.